our final project, we decided to do robot motion planning, which is a subtopic of computational geometry. Our group is myself, Matt, Taylor, and robot motion planning can be loosely defined as the process that a robot goes through to make a decision when it runs into an obstacle in a computed free space. This really just means that the robot will have to calculate its own motion planning or path given by a planar region.
So what's the problem statement? Given a start and end point, we want to compute the optimal path that can be executed so that the robot does not collide with any of the obstacles in a given plane. The only problem is that this plane in specifics is a static one. So if there's changes in the environment, this algorithm won't work. What are the steps to do this? We calculate the free space of the given plane. We then can configure the roadmap and we compute the optimal path. Applications. So why do we care? We can compute problems that in the past have been very hard or difficult to compute, especially for robotics. We can drastically improve the robot functionality and the productivity, which is a greater return on investment on the robots. And we can have accelerated robotic evolution within the last 30 years.
So for the algorithmic solution, we want to compute the optimal path from a start and end point anywhere within the given plane. And like Emma said, it's a static environment. And this just means that the objects within the plane are not going to move. So we must compute the free space first, and this will give us our environmental plane. And what the real result from computing the free space is a trapezoidal map that's shown in the top picture. And from that trapezoidal map, we can then translate it into generating a roadmap. And basically the roadmap is just points in the middle of each vertical line and trapezoid that will be then able to do a breadth first search on. So like I said, the input for the computing free space is just a set of trapezoidal vertex points that will be given to determine the free space of a given plane. And then the output, of course, is a trapezoidal map that we can then use to compute the path. If we look at the pseudocode for this, we first set all the edges to E, and that's just all the edges in the polygon. And then we can compute the trapezoidal map using the trapezoidal map algorithm. And we're not going to get too much into that. Just know that there is an algorithm that you use to compute the trapezoidal map. And then finally, we're going to remove all the trapezoids that lie within inside each of the polygons, basically getting rid of the redundant lines, and then we'll have our final free space trapezoidal map that we can use.
To compute the free space, we start out with the base map, which just contains the area that our robot will be in, the point that we're trying to reach, and all of the obstacles. We begin by extending vertical lines from each of the vertices in the obstacles. We then erase all of the redundant lines to form polygons of free space. So in the third image, the bottom left one, that has all of our free space trapezoids. We then create a road by pointing points into the middle of each free space trapezoid. We then connect each of the free space trapezoids to create all of these roads. So our optimal solution takes the trapezoidal map that we created in the last slide, the start point and the end point, and all of the possible routes that we've created. The output is the optimal path from the start point to the end point that is collision free. If there is no such path available, the algorithm will return there is no optimal path. So we take all of the possible paths that we can perform and we do a breadth first search on all of them. The breadth first search will return the optimal route out of all possible routes.
Okay, so this is our working example. We're going to first draw the environmental plane, and then we're going to go through how we compute the paths. So yeah, this is the environment we're going to be working with for our working example. See on the left, this is going to be our starting point, and then down at the bottom right, that's our endpoint. And so we're going to go through how the algorithm would complete the trapezoidal map. Then we're going to compute the roadmap, and then we're going to show the breadth first search to find the optimal collision-free path.
So first off, we will draw a vertical line stemming from each vertex going to both the min and the max x or y value. And this will essentially allow us to break up the free space and be able to do our next set of computation with the free space.
Next, we remove redundant lines that exist within the obstacles. This is because this is not actually free space and we don't want to move through it despite the fact that it is a trapezoid. We don't need these, so we just remove them. Another thing of note is that these lines are not actually straight and vertical since we are drawing freehand. In an ideal situation, they would be, but for this example, it doesn't really matter since we're just trying to show the functionality. Next, we want to remove any lines that aren't directly connected to a vertex. This will make our trapezoids more accurate and easier to navigate through. As you can see, this one is not directly connected to a vertex, it just passes through. This is another redundant line that we can just remove.
Okay, so to begin creating the road path, what we do is we start by placing a point in the middle of each free space trapezoid. And so we go around putting points in the middle of each free space trapezoid.
Again, this is like free drawn. So please do not kill me on this. Like Emma said earlier, in a perfect ideal algorithm, all of these would be perfectly in the center.
Okay, so now that there are points in the middle of each free space trapezoid, and keep in mind this is free drawn, so it's not going to be exactly accurate, but in a actual use of this, it would be computer generated and calculated, so it would be perfect. But since we're doing this by hand, so now what we'll do is you draw a point or a line from the start point to the middle point of the first free space trapezoid. Then you would connect a line from that point to a point on the edge that is closest to the next free space point. So you would go one straight to the right, and there would also be another line going up and to the right to hit that other free space trapezoid. You would then connect those points to the middle of the free space trapezoid point. You'd then continue this process by drawing lines from the middle point to the next edge that is nearest to another free space middle point that has not already been previously visited. So now that all of the possible points are connected, creating many paths, what our algorithm will do will take this as the input, and it will perform a breadth first search on all of the possible routes, and then it will provide us with the optimal route from the start point to the end point that is collision free.
So yeah, that might have been a little sloppy, but you can see the functionality of the algorithm of how we start with a given plane given to the robot. We then go through and calculate the trapezoidal map, and then from that trapezoidal map, we put our points in to configure the roadmap, and then using that roadmap, we use a breadth first search to compute the optimal path. Sorry if it was a little shaky. My first time in MS Paint, but I believe the overall logic of the algorithm is explained thoroughly. So thank you.